So traditionally, we write d sigma to be dy dz, dx, dy. We usually write d sigma because d sigma is an oriented surface element. It is a vector, therefore it has three components. The three components is written dy dz, dx, dy. Actually, this is precisely cosine alpha, cosine beta, cosine gamma, d sigma. Okay, here cosine alpha, cosine beta, cosine gamma, this is precisely the vector n. So because d sigma is n d sigma, therefore if you write n using the directional cosines, so you have this equality. And we denote dy dz, to be cosine alpha d sigma. That is in the three coordinate space. A piece of surface element, if the normal direction is n, normal so the cosine alpha is the angle between the x-axis and the n, and so the surface, the area multiplying cosine alpha is the projection of this piece of surface in yz space, yz plane. The projection in yz plane. Cosine alpha d sigma is the projection of this piece of surface element d sigma on the yz plane. Therefore, the area of this is d sigma, cosine alpha d sigma. So this is where we denoted by dy dz, because it is the projection to the yz plane. Okay. Similarly, for the projection to zx and xy plane. So usually we write d sigma. Go back to our definition of the flux integral. Usually we write the d sigma here by its components, and also if f is given by component wise, PQR. Here PQR are real valued functions. They are the three components of capital F. Then our flux integral can be written as the inner product of f and d sigma. D sigma is dy dz, dz dx, dx dy. Therefore, we have p dy dz plus q dz dx plus r dx dy. Okay. And of course, if you like, you can also write using the second result, that is cosine alpha, cosine beta. Because dy dz is cosine alpha d sigma, so you can also write this as p cosine alpha plus q cosine beta plus r cosine gamma d sigma. Okay, so this is the flux integral of vector valued function or vector fields. We sometimes also encountered integral of this form. Q is a function defined over a surface, real valued. What is this? What is this? So compare this integral, which our previous component form of flux integral. Compare these two, we see that we can interpolate this integral to be the flux integral of a special f, where this f has two zero components. Only the second component corresponding to dz dx, that is the q. Okay, so integral of this form are simply flux integral of such a function, vector valued function. Okay, and of course the other two kinds of integral for p and for dy dz and the dx dy, that is can be interpolated similarly. You can by constructing a particular vector valued function or vector field. Okay, so flux integral is not contained in our textbook, but as a student of mathematics, you could not unaware of this kind of integral. So this is why I take this opportunity to introduce this integral to you. And this is the concept of flux integral. Anyway, this is nothing new. It is simply a convenient way to write a particular form of the usual surface integral of a integrand resulting from a vector field. That is the inner product with the normal vector. Okay. Now, our question is how to compute this flux integral. Of course, you can always go back by the using definition. You can always go back to the usual surface integral. Okay, but it turns out that we prefer to compute the flux integral directly from the parametrization of the surface. That will be much easier. So we have this theorem. Computation of a flux integral. If S is a surface which parametrization R, of course it is oriented. As I said before, any parametric surface can be oriented. Okay, and F is a vector field over S, continuous. Then the flux integral of the vector field is the double integral by substituting the maybe I will write in another more detailed way. Okay, in our argument we omit the variable x or x, y, z. So I need to write this. So fx, or simply write x d sigma. So I need to write, so fx d sigma. This is our flux integral. Here the x is the point on S, which has 3 components or coordinates. X is not a real number because our x is a point in S, and it has 3 coordinates. It is a point in R3. So this is the double integral over the domain of the parameters, that is D. So the integrand of this double integral is substituting the x by the parametrization. Then inner product which Ru and Rv, then du dv. This is the formula to compute flux integral via the parametrization of the surface. And we have a positive and negative sign in front of the double integral. We have a choice because the flux integral depends on the orientation. From this definition, flux integral is the usual surface integral of f inner product which n. If you reverse the unit vector given the orientation, that is, you reverse orientation of n of the surface, you will obtain a negative sign. Okay, so given a parametrization of the surface, this is a normal vector, but this normal vector might coincide with the orientation normal vector or reverse direction. Their direction might be the same or different. So if they are the same, you take positive sign in front of the double integral. If they are negative sign, you will take negative direction. You will different direction. You will take a negative sign. Okay. So where we choose positive sign if and only if this normal vector coincide with the orientation vector normal, has the same direction. Which n? N is the oriented vector for S. So the proof of this theorem is very easy. And from this theorem, you will see that the computation of flux integral is easier than the usual surface integral. In usual surface integral, f is a real valued function, and but for the cross product Ru cross Rv, you have to take the norm. Taking the norm, you will involving taking square and then sum up the square of the 3 components of the vector, and then you need to take the square root. Okay, so this computation are not easy. But for computing the flux integral using this theorem, we don't need to do that. Okay.